Welcome to Module 201E on Capacitance and Capacitive Reactance. In this module, we're going to cover 6 different objectives, including capacitor construction, the factors that affect capacitance, the effects of a capacitor in a DC circuit, what capacitive reactance is, the effects of a capacitor in an AC circuit, and what the power relationship is within a capacitive circuit. The purpose of a capacitor is to be able to store a static charge, and they have a very basic construction and only require 3 separate components. The first 2 components that we have are the metal plate electrodes, and they can be made of any type of metal. These 2 electrodes are going to be where we store the static charge. The third component we need is called the separator, and this is an insulating material known as the dielectric. It not only separates the plates, but it also creates a polarized electrostatic barrier. And the dielectric material determines the voltage capacity of the capacitor. Sandwiching the materials together creates the capacitor, and now the plates can be charged. The separator allows the charges to be held on the plates without anything shorting out. There are a number of different types of capacitors on the market, but they can be separated into 2 different groups, polarized and non-polarized, and they're normally defined by their insulating materials. For non-polarized capacitors, we can use air, oil-filled, paper, plastic film, mica, or ceramic. And those are the most common types that we can find. Non-polarized capacitors are good for either AC circuits or DC circuits, and the terminals are not marked for any polarity. They also typically have a smaller microfarad rating, so the capacitance of these are typically smaller, but they will have a higher voltage rating. A very specific type of capacitor is called the electrolytic capacitor. These types have a very thin dielectric inside, so the voltage ratings are relatively low, and it's important not to exceed the voltage ratings of a capacitor. These can come in both polarized and non-polarized form, however most of them are polarized and are to be used in DC circuits. Keep in mind we can only use non-polarized capacitors on AC circuits. When you're working with polarized capacitors, their leads are always identified in one of many different ways. We can either have arrows on the actual body of the capacitor itself telling you either where the positive or the negative terminal is, or some manufacturers have the shorter lead on the capacitor indicating the negative terminal. In 201E Objective 2, we're going to talk about what capacitance is and also what is going to affect capacitance. Basically, capacitance is the property of a capacitor to store an electric charge or potential difference between the 2 plates, and it is stored within an electrostatic field. In order to understand this, we're going to look at the process of charging a capacitor. Generally, when we have a de-energized capacitor, both plates have what's called a neutral electrical charge, which means all the electrons and all the protons on those plates are an equal number, giving us a net zero balance of charge. When we apply a voltage to our capacitor, we apply electrical pressure, and that electrical pressure is forcing electrons onto one of the 2 plates of the capacitor. Since like charges tend to repel each other, what is happening is that as I force electrons onto one plate, it is forcing electrons off of the other plate due to this natural action of repulsion. The net result is one plate will be a negative charge because it will have excess electrons. The other plate will become positively charged because it is lacking electrons. If I were to increase the voltage applied to a capacitor, I'm also increasing the electrical pressure, which means I'm forcing more and more electrons onto that one plate of my capacitor. This means it's repelling more and more electrons off the other plate. The result is that I've increased my negative charge on one plate and I've increased my positive charge on the other plate. This means the potential difference between those 2 plates has also increased. Generally speaking, whatever source I've attached my capacitor to, it will charge to the same voltage of that source. Keep in mind, if I keep increasing the voltage applied to this capacitor, eventually I'm going to force electrons through the separator, and that will destroy the capacitor. The amount of charge that a capacitor can hold is rated in farads, and a capacitor has a rating of 1 farad if it can store 1 coulomb of energy for every volt across it. A farad is a very large unit, so most capacitors will be rated in the microfarad or the picofarad range. We represent capacitance with the symbol C and is always measured with variance F. The amount of capacitance that a capacitor can have are affected by three different properties, the first of which is the plate area. The larger my plate area, the more electrons I can hold on that plate. Therefore, more charge difference I can have between the two sides. My plate area is directly proportional to the amount of capacitance I can have. The second factor I have is the distance between the plates. The less the distance, the more effect my electrons are going to have on each other. So when I load electrons onto one plate, they will repel more electrons off the second plate if I can minimize the gap between those two plates. The more spacing I have, the less effect those two plates are going to have on each other. So less distance between plates, the greater the capacitance I have. Thirdly, the type of dielectric compound I have will also make a very large difference. When I change that compound out, I can also change the capacitance of my capacitor. When it comes to the dielectric material's properties, there are two terms that we need to be aware of. The first one is the dielectric constant, and that is a rating of how well a material can polarize and store a charge as compared to air. So air becomes our benchmark. The higher the constant, the better the capacitor. The second term that we need to be aware of is the dielectric strength, and this is the insulation strength of a material, and it's measured in kilovolts per millimeter. This is how much voltage the material can withstand before breaking down. A capacitor's voltage rating is based on the dielectric material that it is made with. If the capacitor voltage rating is exceeded, the dielectric material will lose its insulating properties and it will short out. This is also known as dielectric breakdown. Capacitors are generally labeled with either working volts DC or with an AC voltage and the frequency attached to it. Our next objective is to look at the effects of a capacitor inside a DC circuit. When we put a capacitor into a DC circuit, the capacitor is going to gain enough charge to equal the source voltage. Once the capacitor reaches the same potential as the source, the charging will stop. To begin, with our circuit in the off position, our capacitor will have 0 volts across it. When we close the switch, we start to charge the capacitor, and now we start to see a polarity across the capacitor as well. The capacitor will continue to charge until it reaches the potential of the battery, but the charging does not happen at a steady rate. What we find is that we will rapidly charge the capacitor to start, but as the capacitor's voltage starts to match the voltage of the source, the charging will slow down. After the capacitor is charged and we open up the switch again, we find that the charge stays inside the capacitor. Without a discharge path, a perfect capacitor could remain charged indefinitely. When we put a load into a charged capacitive circuit, the capacitor now will supply energy to the load. The electrons will leave the negative side of the capacitor, travel through the load, and go to the positive side in order to balance out the charge. When the switch is closed, the capacitor will discharge. The amount of time it takes the capacitor to discharge will depend a lot on the resistance and the capacitance of the circuit. The larger the capacitance, the longer the load is supplied with energy, and the higher the resistance, the slower the electrons are going to travel through the load. Once the capacitor is discharged, then the electrons stop flowing since we have a balance of charge between the two plates. Here is a more typical charging and discharging circuit for a capacitor. In the charging cycle, we have electrons traveling from our power source or our battery to the plates of the capacitor itself. And as the electrons accumulate on the negative plate, they're pushing the electrons off the positive plate. So we see that the charge goes up through the load, then back to the source. When we discharge, we now close the switch on the other side, which allows the electrons to go off the plate that is negatively charged, flow through the circuit, and now they go down through the load to return back to the positive plate. The current flow on charge and discharge of a capacitor will be in opposite directions. When we look at the graph of the voltage and the current of a charging capacitor, we can see that there's a non-linear aspect to this. We have a sudden uprise in the voltage up to the point where the voltage peaks, and we also see a very high current at first, but that drops off as the capacitor starts to charge more and more. This would indicate that we have a slower current as our capacitor reaches full charge. The time it takes to reach full charge can be divided into 5 different time constants. And just as we saw with inductors, each one of those time constants is worth 63.2% of the total available rise that is left. The time constants are not only applicable to the voltage rise, but also to the drop in the current. We can also see the same time constants existing in the discharge cycle as well. In a discharge cycle, since my current is moving in an opposite direction as we saw before, I would have a negative current flow, and that will taper off to 0 over 5 time constants. I can also see my voltage drop from maximum voltage down to 0, once again over to 5 time constants. When it comes to calculating how long our time constants are, we use the formula T is equal to R times C. This means that both resistance and capacitance have a role to play in how long those time constants are. In our first circuit, where we have 5 ohms and 10 microfarads, each time constant has a value of 50 microseconds. If we look at our second circuit, we have doubled the amount of resistance into the circuit. What we can see is that we've also doubled how long each time constant is. Now, one time constant equals 100 microseconds. The reason for this is simple. With larger resistance, I've slowed down the electron flow. Since I've slowed down the electron flow, it's going to take longer to either charge or discharge my capacitor. Also, when I look at my third circuit and compare it to my first circuit, I can see that I have twice as much capacitance this time. 20 microfarads compared to 10 microfarads. And once again, between the first circuit and the third circuit, I can see that my time frame has doubled again. And this is because since my capacitance is so much larger, it'll take me longer to fully charge that capacitor. Therefore, it's going to take more time. Both resistance and capacitance are directly applicable to what the time constant time frame is going to be. And we're now going to look at the term capacitive reactance and how that affects our circuits. As a capacitor charges and discharges, it opposes a change in voltage. And when it's connected to an AC supply, the opposition to changing voltage is constant, and it causes a subsequent opposition to current. This opposition to current is called capacitive reactance. Capacitive reactance is measured in ohms and is represented by the letters XC. Just like our XL with our inductive reactance, we now have XC with our capacitive reactance. The two factors that affect capacitive reactance are both frequency and capacitance, and they both affect capacitive reactance in an inverse way. As we look at our formula, XC is equal to 1 over 2 pi FC. This applies to our AC circuits. If my frequency were to increase, my capacitive reactance would decrease. And if my capacitance were to increase, my capacitive reactance would once again decrease. This is what makes them inversely proportional. Whenever we use this formula, we need to make sure that we are converting our microfarads to farads. Therefore, with my 66 microfarads, I need to move the decimal place 6 places to the left, which would mean this is 0.000066 farads. And that is the number I need to have inside my formula. The other way I can do it is to modify my formula slightly. By taking the 1 and replacing it with a 10 to the power of 6, I can now use 66 microfarads inside my formula, and it will still work out properly. This does my conversion for me. Using either version of the capacitive reactance formula, I would like you to solve this circuit. Pause the video, and when you have the capacitive reactance, resume the video and we'll check your answer. In this circuit with a supply of 120 volts and 60 hertz and a capacitance of 66 microfarads, I should have a capacitive reactance of 40 ohms. I can now use my capacitive reactance and my source voltage with my Ohm's law to calculate what my current is. 120 volts divided by 40 ohms equals 3 amps of current. Let's move on to our second example. Here we have a circuit with 29.4 microfarads of capacitance. Also, take note that we've dropped the frequency from 60 hertz down to 40 hertz. Use your capacitive reactance formula, pause the video, and calculate the capacitive reactance. When you have your answer, resume the video and we'll check to see if it's right. The capacitive reactance in this circuit is 135.34 ohms. Since we lowered our capacitance and we lowered our frequency, they are both inversely proportional to my capacitive reactance, which means that my capacitive reactance would be higher, which we can see that it is. If we have a circuit where we have the capacitive reactance, but we wish to find our capacitance, we can transpose our equation in order to find this. To properly transpose this equation, we would simply exchange the XC and the C. Now we can use this formula to calculate what the capacitance of this circuit is. Pause the video, calculate the capacitance, and then continue. We find that the capacitance of this circuit is 35.37 microfarads. Make sure you take the time to review these formulas and understand the relationship between capacitance, capacitive reactance, and frequency and how they affect each other. We're now going to look at 201E Objective 5, and we're going to discuss the characteristics and the effects of an AC capacitive circuit. Since capacitance is the opposition to a change in voltage, when we have a capacitor in an AC circuit, the voltage tends to lag the current. We're going to compare this to a typical resistive circuit. In a resistive circuit, it is in phase, meaning that it peaks and crosses the zero line at the exact same time. In a purely capacitive AC circuit, we find that voltage is going to lag current by 90 degrees. The reason this happens is that when we have the peak in our voltage, that means that my source and my capacitor are at the exact same potential, which means that there's no current flow. My current will be at zero. However, when my voltage is changing, that's when we have maximum current flow. Therefore, my current should be peaking right around the time that my voltage is zero, because that's the maximum point of change. Just like inductors, we're depending on the change in voltage in order to create this reaction. With a capacitive circuit, we find that current leads voltage, and we can use the acronym ICE in order to remember that. For both capacitance and inductance, we have the memory trick Eli, the Iceman. Eli is for inductance because the L represents the inductance. Ice is for capacitance because the C represents the capacitance. In inductance, E is before I, which means voltage leads current or current lags voltage. In capacitance, ICE, I is leading voltage or voltage lags current. Remember this acronym and it will help you identify what different circuits are. If we're also to compare our sine wave with our phasor diagrams, what we would find is that if voltage was our reference, current would be at 90 degrees. And this would indicate that current is leading voltage by 90 degrees. If we had current on our reference line, then we would find voltage at 270 or negative 90 degrees, which is showing that voltage is lagging current or current is leading. Remember, with phasor diagrams, it all depends on perspective. What is on the reference line and how I indicate a capacitive circuit is making sure I place the current phasor 90 degrees leading to my voltage phasor. Our last objective in 201E is to look at the power relationships of a capacitive AC circuit. Just like inductive circuits, capacitive circuits create reactive power, or RQ. With our reactive power, once again with our capacitive circuits, we'll have twice the frequency of what our supply circuit is going to be. This is because every time either current or voltage crosses the zero line, my reactive power is also going to be zero. This means that I'm going to have twice as many cycles for my reactive power than I am for my voltage or for my current. Anything that is above the zero line is me building that electrostatic field. And everything below the zero line is me releasing that electrostatic field. Remember, with reactive power, it doesn't actually leave the circuit. All we're doing is building up that energy inside the circuit and then releasing that energy back into the circuit again. I know there's a lot of information in this module to understand what capacitors do and how they do it. But by the time you're finished with this module, you should be able to describe how capacitors are built, what different types of capacitors there are, and what different applications that we can use them in. You should also be able to define what capacitance is and what the effects of a capacitor on a DC circuit are. Make sure you're taking the time to understand the time constants. You can also describe what capacitive reactance is and the characteristics and effects of an AC capacitive circuit. And lastly, you need to be able to identify and describe power relationships inside the capacitive circuit as well. You've now reached the end of 201E. Please return to Blackboard and complete the worksheet and do the knowledge check. Once you're done that, you can continue on to 201F.